In this example, we're going to look at how we can use cylindrical coordinates to describe regions of three-dimensional space. In particular, in this problem, the region enclosed by the surfaces z squared equals x squared plus y squared, and x squared plus y squared is equal to 1, with z being greater than or equal to 0. To help us get started, let's identify these surfaces. So the first one here, if we go back and look at our notes on quadric surfaces, we see this is just a cone. And the second one is the extension of a unit circle to R3, which is a cylinder. We'll also note that z greater than or equal to 0 means we're above the z equals 0 plane. Let's try and sketch this now to get a sense of what this region is going to look like. Starting with the cone, we've got these diagonal lines that come out, and we're only going to need to go up to z equals 1, because at that point this thing intersects with the cylinder of radius 1. And then we also keep in mind that we're sitting above this plane z equals 0. So the region we're interested in describing is the region that sits outside this cone and inside the cylinder, but above the plane z equals 0. Since we want to describe this region in cylindrical coordinates, let's start by describing each of these surfaces in cylindrical coordinates. So for the cone, which in Cartesian coordinates is described by z squared is equal to x squared plus y squared, becomes z squared is equal to r squared, since if you recall, the cylindrical coordinate r is defined such that r squared is equal to x squared plus y squared. Since z and r are both positive, this is equivalent to z is equal to r. So that's the equation of the cone in cylindrical coordinates. For the cylinder, this is described in Cartesian coordinates by x squared plus y squared is equal to 1. And that just becomes r squared is equal to 1. Or again, since r is positive, r is equal to 1. That's how we can describe a cylinder in cylindrical coordinates. The coordinate z doesn't change from Cartesian coordinates to cylindrical coordinates, so we still have our plane being described by z equals 0. Let's call this region inside here R. How can we describe R? Well, you can see that we have circular symmetry here about the z-axis. So something we can take advantage of here is the theta coordinate, in that if we can just describe a sheet here, sort of a slice through this cylinder of this region, then we can sweep out the full region by letting theta run from 0 to 2 pi. So let's just focus on that section. So we've got our z-axis, we've got the edge of the cone, which is described by z is equal to r. We've got the edge of the cylinder, which is described by r is equal to 1. And we've got the plane at the bottom, which is described by z is equal to 0. And we're trying to describe the region in here. We can do this by writing down a series of inequalities. So we can say r is equal to all points r theta z such that, and now we have to put constraints on r and z. For reference, let's label on here that this is 1 and up here is also 1. So we can't just let r and z run from 0 to 1 or we would get this entire square. We only want the triangle. So we can actually approach this two ways. One way is to imagine that we have this radial distance that we're sweeping out, and we're sweeping radially from this line, r is equal to z, to r is equal to 1. But z we're going to let run from 0 to 1, and we're going to have this constraint that r only runs from z to 1 to take care of the fact that we only want this triangular region. So what does that look like? Well, we would have r range from z to 1, and we'd have z range from 0 to 1. And now finally, we would let theta sweep out around the full cylinder from 0 to 2 pi. So that's one way to answer this question. Another way would be to approach this by putting a constraint on z. So as if we were going up starting at z equals 0, up to the line z equals r. So in that case, again we would describe it as a collection of points r, theta, z, but our first constraint would be that z runs from 0 up to the line z equals r, and now r wouldn't need to be constrained. And finally, we'll sweep out theta from 0 to 2 pi. So that's another equivalent way of describing this region. Both will work, and later on when we're talking about doing integrals over these regions, we'll be using these descriptions to come up with the limits of integration. And so we might actually find that one description is preferable over another, depending on what we're integrating. Alright, that's it for this example. Thanks a lot.